We'll start a new topic altogether. So the question that I want to focus right now are the real magnetic materials. What I mean by the real magnetic materials, the commonly available magnetic materials which are ferromagnetic. Generally we call in our everyday parlance materials to be magnetic which are really ferromagnetic. So why do ferromagnets exist? Because we've seen that there is an exchange interaction. But the exchange interaction, the integral which is called J, which is an overlap integral, this goes down to zero very rapidly with distance. So when you have a material such as iron, so the iron is a metal. Let's consider iron. Iron is a metal in which there are cations, ions, at fixed sites on a crystal structure. The crystal system for iron is BCC. So this is a BCC lattice, and on each lattice point there is a single iron atom. So this entire crystal spans out in 3 dimensions. And then there are free electrons. So now, why is iron magnetic? One possibility is that the ions, now each ion itself can be magnetic. It can have a spin which comes out from the spins of the electrons. Correct? It could be some J. Now we can calculate what J for an ion is based upon the number of unpaired electrons in the valence shell and which orbitals they exist in. So we can use, for example, the Hund's rule to find out the number of unpaired electrons, and we then find out which orbital do they exist in. These are d orbital electrons. So we know the orbital angular momentum L. So we add up their angular momenta, and then we couple the angular momentum to a spin-orbit interaction to find the overall J of that ion. But that's just one ion. How does the overall material become magnetic? And that's the big question. So, ferromagnetism means that all the spins are aligned in a domain. So, how does one ion at a fixed crystal site communicate its direction to a neighboring ion? That's the question. So, why does a ferromagnet exist? No doubt, each ion can have a spin, a J, which can be calculated from basic ideas. But then, why is the material ferromagnetic? Why are all the spins in a particular domain aligned with one another? It can't be the exchange interaction, because the exchange interaction requires an overlap of electrons belonging to different ions. Right? Remember there was a phi1r1, phi2r2, phi1r2, phi2r1. So these are orbitals belonging to different sites. And these ions are far apart. And the exchange interaction is a Coulombic interaction. It drops as 1 over r squared. So the exchange interaction direct exchange interaction cannot really exist between ions, unless you have this higher order exchange interaction pairs like double exchange or super exchange. So why is it ferromagnetic? It can't be the electrons on its own. So far what we've discussed, we've looked at free electrons, and if anything we have seen 2 kinds of effects for free electrons. One is the polyparamagnetism. That's paramagnetism, a very small susceptibility. And the other is Landau diamagnetism. It's of the same order of magnitude as the poly term, and it's diamagnetic. So what we've studied so far cannot explain ferromagnetism in most of the ferromagnetic materials. So we need to look at something else. So that's something else. We need a model for that. That model is called the Stoner model. So, but in order to build up the Stoner model, I have to build 2 kind of prerequisites for that. One is the tight binding Hamiltonian and the other is the Hubbard Hamiltonian. So far we have not really looked at the interaction between electrons. Only the very first few lectures when we were studying exchange interaction did we look at the interaction between an electron and a proton and two electrons, correct? But we haven't gone beyond that. So now we want to include interactions between electrons into our system. And these interactions can be strong, they can be weak. Okay? So this is what we're going to look at now. Now we're going to look at strongly correlated electron systems. The basic idea I want to kind of approach is, why are certain materials ferromagnetic at all? What is the underlying principle? The underlying principle is the Coulombic repulsion between electrons. So how does that result in ferromagnetism? Remember that iron is one of the most magnetic materials. Its permeability is of the order of thousands, tens of thousands. Excuse me. Okay? So, and the polyparamagnetism effect is of the order 10 to the minus 5. So this is 7-8 orders of magnitude larger than polyparamagnetism or the other effects that we've seen so far. Where does this come from? So in order to build up this discussion, I like to kind of introduce the idea of the tight binding Hamiltonian. Now, as you know that the exchange interaction, this Hamiltonian minus 2 Jij Si dot Sj, this is a toy Hamiltonian, right? It explains exchange phenomena. Okay. Likewise, there are other toy Hamiltonians as well. One example is Ising Hamiltonian. This is not a dot product, this is just Ising. Ising Hamiltonian. We have also seen Hamiltonians of this kind. Si plus Sj minus plus Si minus Sj plus. This is raising of the angular momentum on one spin and lowering on the other spin and so on. Right? So we have Hamiltonians of this kind as well. So all of these are toy Hamiltonians. They describe phenomena. Now the tight binding Hamiltonian is another very useful Hamiltonian, especially when it comes to describing band structure in solids. So the basic idea of the tight binding Hamiltonian is that electrons are tightly bound to certain ions or certain sites. Okay, so if you have two hydrogen atoms that are far apart, the hydrogen molecule has not yet been formed, then there's an orbital with this hydrogen atom and an orbital with this hydrogen. So each electron is bound tightly to its respective nucleus. And when the two nuclei come closer together, they form a molecule. And then you get a linear combination of atomic orbitals. Right? So tight binding Hamiltonian is when the electrons do not interact with one another, but the electrons can hop from one side to another. So if I were to write down the Hamiltonian, the tight binding Hamiltonian, this is what it might look like. H is minus. Suppose you have, now I just want to use a second quantization formalism straight away. So when we discussed magma, we first looked at the spin orbital angular momentum, and then we did a Holstein-Primakov transformation to converge to the bosonic creation and annihilation of it. Right now we're going to directly use the second quantization. So the Hamiltonian, the second quantization form is given by, so we have two sites, two distinct sites, I and J. And each of these sites is an ion perhaps, and electrons can live on each site, and these electrons live in certain orbitals. For example, this could be a p orbital here and a p orbital here. Okay, this would be p orbital here, a d orbital here. And an electron lives in this orbital. It can have a certain spin, but the tight binding Hamiltonian presupposes that a process can occur in which this electron with a particular spin in this orbital attached to atom I can hop on to site J, go to this orbital and attach itself to J's nucleus while preserving its spin. Okay? So it can hop from site to site. And we assume that there's only one orbital located on this site, and the same, and then perhaps a different orbital on this site. Okay? So one orbital per atom. And the inverse process can also take place. That is, you can have a hopping from J to I. And there's also the possibility that the spin of the electron is pointing down. And the spin is preserved as the hopping process unfolds. So no spin scattering is allowed. So if you want to write the Hamiltonian for this process, there is a certain amplitude that this hopping between sites A and J can take place. So when an electron is on this site, being in a particular orbital means that it has a set of quantum numbers, M, L, ML, and all of these specify the spatial quantum state. So it has a certain quantum state here, alpha, and a certain quantum state here, beta. So you can either consider this to be a quantum state, alpha, beta, or you can say that the electron is in a particular orbit, because an orbital is nothing but a quantum state. So if you were to write down this process in terms of second quantization form, there is a certain amplitude, a probability amplitude, a complex number that kind of controls this. Let's call that T. And this is hopping between two sites, I, J. So we kind of identify the parameter. And the two quantum states alpha and beta or orbital. So quantum state is orbital. All the quantum numbers besides the spin, okay, which we generally call the orbital. But then there is also spin. Spin is also a quantum number. So for spin, I write the symbol sigma, which will be up or down. So there is a particular amplitude associated with this process. Now, if an electron is annihilated on this site, it's created on another site. So suppose the electron is annihilated on the ith site and created on the jth site, or annihilated on the jth site and created on the ith site. Right? So it's just one electron that is hopping around. So we can write down Ci sigma, so spin, Ci alpha, spin, right? Sigma for the spin. There is an annihilation and there is a creation. Right? And then you sum up over all i's, all j's, all alphas, all betas, all sigmas, right? So this is the Hamiltonian, the tight binding Hamiltonian. So it's just a creation of an electron in a quantum state, the annihilation of an electron in the quantum state beta on site j spin sigma, accompanied by the creation of an electron on site I, maybe a different quantum state alpha, same spin sigma, right? And then there's a certain probability amplitude that this happens. This is just a convention. Then you sum up over all the sites that are involved in this hopping process. You sum up over all the quantum states and the two kinds of spin states, up and down. This is a tight winding Hamiltonian. Now, given a Hamiltonian, we would like to find the energy spectrum. This is how we've been proceeding all the way through where we discussed magnons, etc. So the next question is to write down the eigenstates. Yes, please.
सर हम ये assume कर रहे हैं कि ये हाइड्रोजन एटम के आयन्स हैं.
हाइड्रोजन नहीं, कुछ भी हो सकता. हाइड्रोजन तो नहीं.
तो स्पिन प्रिजर्व करने के लिए हमें ये नहीं करना पड़ेगा, मेक श्योर करना पड़ेगा कि एंटी सिमेट्राइजेशन जो है वो हमेशा मतलब फुलफिल हो रही है.
वो होगी क्योंकि this is a homework problem when I prepare homework number 6. So if I have this vacuum state and I kind of have on spin, right, something of this kind, Ci alpha, any quantum state can be produced in this fashion. So I can create any number of, so there's a particular representation called the occupation number representation. So if I start off with the vacuum state, I can create either 0 or 1 spin on the ith location in a certain quantum state alpha in a certain spin, and I can create an electron at site G, quantum state B, and V spin, right? And I can do this for all values of I, J, alpha, beta, right? So this will give me all the quantum states. Now, by looking at the properties of these fermionic operators, which means that they anti-commute. So remember question in the midterm exam. That will ensure that the overall wave function that is produced is going to be anti-symmetric under exchange. Okay, so I'm going to give this as a homework problem. So anyway, this is the tight binding Hamiltonian, and the symmetrization postulate, by the way, will always be satisfied. Now what we would like to do, we would like to solve this for an arbitrary geometry which is called a crystal structure of sites. So look, let's first of all try to solve this tight binding Hamiltonian for the 1D problem. And when I solve it for the 1D problem, I also explain what bands are. What are band insulators, what are Chern insulators, etc. So first of all, let's look at the 1D problem. In a 1D problem, I have a chain of atoms or ions, right? Be very large, but still finite number of atoms on a chain of length L. On each side, I have some orbital. I'm drawing a kind of a dumb shell orbital, but remember it could be any orbital, S, P, D. So it's a combination of quantum numbers, and it's the same orbital on each atom. Alpha, no betas, just one alpha. And there is one orbital per atom. Okay? One orbital per atom. And the unit cell for this one-dimensional problem is just this bit, right? This is a unit cell. Suppose this distance is A. The cell dimension is A. The overall length is L. There are capital N sides, so I have L equals NA. This is the length of this chain. Now the problem is very similar to phonons, and the problem is very similar to magnons in a sense. Remember that magnons and phonons are bosons. Here we have a slightly different scenario, so we get a different dispersion relationship. So now what we kind of have is just one orbital which we label as alpha per atom, and the electrons, which are spin-full particles, they are fermions. And we assume that each electron can only hop to its neighboring site, in the positive direction or the negative direction, only to its neighboring site, only to its nearest neighbor. There is only two neighbors, the left or right for each site. And the amplitude for going forward and backward is the same, it's p. Okay, so all the t's are the same. So the Hamiltonian for this system will now become minus t sum over. Now I have c I. Now I don't need to write alpha because alpha is same. So ci sigma dagger cj sigma, and I want ij to be nearest neighbors. I and j are of course not the same, and I want to sum up over both kinds of spins. This is my tight binding Hamiltonian, correct? Now what I would like to do, I would like to do a Fourier representation of this. Can you please write down the Fourier representation of this? Attached to one side, it will also have some energy. So this is the energy due to the hopping, but it will have some native energy when it is bound to an atom, when it's in its atomic orbital form. So we also need to include that term as well. So that term, suppose when electron is attached to its particular site in a particular orbital, the energy is Ea. And then we would like to also have the sum over all sites. This is the energy per orbital. Right? So we also need to have the sum over all the sites I. Okay, so what is that? Ci dagger Ci. That's simply the number density on each site. Correct? Now can you use the Fourier transformation to, if you use a Fourier transformation on this side, it will simply result in Ck dagger Ck. Okay, so this is easy. Can you please convert this to the Fourier representation? Is given by 1 over n c I sigma e minus I k r I sum over I, right? This we know. And the inverse for this is that c I sigma 1 over n is sum of k's d k sigma e plus I k r I. Correct? This is the inverse Fourier transform. So I just insert this thing in here. So I get minus t. The first term, this term here, is minus t I j sigma, the two kinds of sigmas, sum over k's, k prime ठीक है, और उसके बाद हमारे पास this becomes d k d k prime sigma e minus I k r I e plus I k prime or j. Correct? Now I need to with 1 over n as well. Okay? Now what I need to do is if I look at this term over here, I can just kind of add and subtract in terms. Minus t, nearest neighbor is ij, sigma k prime 1 over n d k sigma dagger t k prime sigma e minus I k r I e plus I k prime or I e minus I k prime or I and e plus I k prime or j. Correct? So by the way, one thing I need to. So this is I and J. I and J are different. So for example, this could be C1 dagger C2, but it also could also be C2 dagger C1, right? So I can also I need to add the Hermitian conjugate of this over here as well, because it's a nearest neighbor interaction. Right? Now if I look at these two terms, this will give me E minus I k minus k prime or I. This is going to give me E minus I, let's put it E plus I k prime or j minus r I. ठीक है? Now the sum of this over I can replace rj minus ri by some delta, which is rj minus ri. Since I have the Hermitian conjugate, I just need to consider this delta in one direction. So this delta is the spacing between rj and I. Remember in crystallography, or when you talk about crystal structures, the translation vector is from here to here. You do not consider this translation vector because that's understood to be there. So that's why I put a Hermitian conjugate here, which really means that I need to consider only one direction, and the Hermitian conjugate takes care of the other direction itself. Now the summation of this term, so I have now changed the variables. Instead of ri, I can introduce this new variable, delta. So when I look at this term overall, I get minus t summed over sigma k prime 1 over n d k sigma dagger dk prime sigma. So 1 over n. Now the sum of this over i's, right? So I can just pick up the i's from this pairs. Pick up all the i's. You can pick up all the i's and have this to minus I k minus k prime ri. This goes like this, and I'm left with the deltas which correspond to the nearest neighbors. So now I've changed the variables from ij to I deltas. I'm left with e I k prime deltas. And I also have the Hermitian conjugate to it. Whatever I have over here, I'll have a Hermitian conjugate to this. Okay? So now if I what is this equal to? It's equal to drag delta function times n. Drag delta function with variables k prime. So I can just kind of suppress one of these indices. I can just write k sigma minus t d k sigma dagger dk sigma, right? N just goes away. This is for the nearest neighbors. The delta is for the nearest neighbors. E I k delta plus a Hermitian conjugate. Okay? This becomes minus t sum over k. Now the Hermitian, there is only one delta in the system. That's plus a plus x, a in the x direction. Only one delta in the system. Okay? So if I take the Hermitian conjugate of this number, this is a number operator. Its Hermitian conjugate is Hermitian. Number operator is Hermitian. And I take the conjugate of this. This is becomes e minus I k delta. Right? So I get 2 times cosine of k dot delta dk sigma delta dagger dk sigma. So this is my Hamiltonian. Overall, if I were to write the tight binding Hamiltonian for the chain, this becomes minus t 2t sum over all k's. Of course, sum over sigmas, and there are 2 kinds of sigmas. Sum over all k's, sum over the 2 kinds of sigmas. Cosine of k dot del is simply ka, because delta is a in the x. So this is a in the x direction, and k is also one dimension. It's a one dimensional problem. So this is k in the x direction. I can put a small kx if I want, but I don't need it because it's just one. Right? So this is cosine of Ka plus, of course, the energies Ea, and all of this dk sigma dagger dk. So this is a tight binding Hamiltonian for a 1D chain. What's the dispersion relationship? It's in the harmonic oscillator type form, the normal coordinates. This much is the half h power omega t. This much is the energy, isn't it? So the dispersion relationship turns out to be E as a function of k is minus minus 2t cosine of Ka plus Ea. Correct? Alright? ठीक है? Let's plot this. T is some amplitude. And we in the model it's assumed that this T is real. So if I plot this kind of structure, here I have K. This is my K axis. Here I have energy. Now what I'm going to plot is really E K minus Ea. So I'm going to lower down the energy. So with respect to the atomic orbital energies, that's what I'm going to plot. Otherwise the entire curve is shifted above or below by Ea. So when I plot this, I need to plot this minus 2t cosine Ka. So what does this plot look like? क्या शक्ल होगी इस प्लॉट की? It's a cosine function, negative. और K is pi. Right? आगे भी होगा. ठीक है? So this is what this function looks like. This is the dispersion relationship. Now, from how many of you have taken a course on in condensed matter physics? All of you, solid state physics. So now this is a dispersion relationship. This is the k-axis. So we're plotting things with this in the reciprocal space. Now, since there are n points in the real space, there will be n points in the first Brillouin zone. And the first Brillouin zone extends from minus pi a to plus pi. So this is the first Brillouin zone. Right? This is the first Brillouin zone. And all those n points in the real space become n points in the k space in this first Brillouin zone. Okay? And this dispersion relationship is periodic with period 2 pi over a. Correct? That 2 pi over a is called the reciprocal vector G. So you shift this by 2 pi over a, you get repeated back. So generally, one possibility will be it's sufficient to plot everything just in the first Brillouin zone. If you plot everything beyond it, that's what is called the extended zone scheme. But this is the reduced zone diagram for this dispersion relationship. Now there are n points. So, and we know that in 1D, the spacing between two successive k points is 2 pi over L. And there are n such points. So these are closely spaced points. N such points, right, in the first Brillouin zone. N of these. And they're really closely spaced. And the spacing between any 2 points is 2 pi over L. Right? So if I multiply 2 pi over L by, so if I overall look at this length of the first Brillouin zone is 2 pi over a. So 2 pi over a divided by the spacing between these 2 points will give me the total number of points. So at L over 2 pi. This is L over a, but this is simply the number of points in the real space. And remember that in this structure, the unit cell has just one kind of atom. It's a kind of monoatomic unit cell. One atom per lattice point. So all of those endpoints are kind of spread out in this space. Now suppose I have in this 1D chain, there is an atom that contributes just one electron. Suppose it's a metal, like sodium, 1D sodium, just imagine. And each sodium atom contributes one electron. There are n points inside the first Brillouin zone, remember? So there are how many, like this sodium is monovalent, it has valency 1. So one electron is coming from each sodium atom. So there are n electrons. So this, where would those electrons lie on this energy diagram? In the first Brillouin zone. Of course, they have to go to the lowest energy available to them. And there are n such points. So how many electrons do we have? N. So how many? We have n points. Where will all those electrons be spread out? In all of this? No. Because each point, the K space can harbor 2 electrons. Because of the polyation. So all those n electrons, it's a monovalent ion. They will come in this lower half. This part of the band will be populated. This energy is actually EA. Okay? It's like a Fermi energy as well. So this is the maximum occupied level at 0 kelvins. What is this width in the energy space? It's 40. Minus 2t plus t is 40. Right? So this is called the width of the band, and this is called a band or a branch. Right? So a band is a collection of K points which are inhabited by these electrons. And the width of this band is 40. Now T is the hopping parameter. T large, hopping amplitude large, the band is wider. Hopping parameter is small, the band is kind of thinner, tighter. So also the band width of the band width. And if there's a monovalent ion, half of this band will be filled. Now what does half of a band being filled mean? So if I draw this band again, half of it being filled means being filled up to this level. It's a monovalent situation. The question is whether this will be a conductor or an insulator. If I apply a tiny electric field, what's going to happen? So this is the Fermi energy now. So if I apply an electric field to this 1D tight binding chain, what's going to happen? First question, will conduction take place? क्या होगा कैसे होगी कंडक्शन? क्या होगा इलेक्ट्रॉन्स को? क्या होगा खड़े रहेंगे इधर ही, फिर क्या होगा? एक साइड से नीचे आ जाएंगे, ठीक है, स्विंग से हो जाएंगे, क्योंकि the electric field supplying an electric field, that's how conduction takes place. Electric field is in a certain direction. That direction will cause the energy of electrons to change, right? And they will accelerate. They will gain a momentum in a particular direction. So this is the momentum axis. So some electrons near the Fermi energy will have a higher momentum, but this is at the expense of these electrons. So they're kind of so the entire thing shifts like this. And production is there. Neighboring free levels are available in the same band. This band is half filled. The filling of this band is 1/2. It's half filled because of the monovalent ion. Okay? So this is a metal. If you had a divergent situation, the divergent case, for example, a chain of magnesium atoms, 1D chain of magnesium atoms, and these are the edges of the first zone, then this is going to be completely filled. because now there are two n electrons and n states, each state will have two electrons of such things. So the band is completely filled. A completely filled band represents an insulator. This is an insulator. So if you kind of apply an electric field to this, no conduction can take place in a direction parallel to the prior electric field. Sometimes, due to other effects, topological effects, conduction can take place perpendicular to the prior electric field. A transverse current can flow. Such an insulator is called a Young insulator. Okay. Now I have the question is, what if we change the scenario a little bit and we have kind of two kinds of atoms per unit cell. So this is one atom, this is another atom. So now we have a divalent atom. The unit cell still remains of length A, but now there are two atoms in the unit cell. Right? So it's still a one-dimensional iron. So iron will have as a body centered in 3D, but just imagine two atoms per unit cell. Now what's going to happen in that case is that if I were to draw a diagram, E Five and eight minus 5.
So in this case, so the structure will go like this. So if for a monovalent atom, this is what the band diagram looks like.
Now for divalent, what's going to happen is that it's like
This is just like a diatomic change, a chain.
diatomic.
This is going to come down a little bit here.
Down a little bit here,
And beyond this point, this is going to start from here.
so it's going to extend, but there's going to be a gap here.
And this gap can be found by second order perturbation theory. If I were to teach quantum mechanics 2, this is the thing that I'm going to explain.
So this gap is
Form
formed.
over here.
Okay. Now this is the extended zone scheme. If I bring this
Backed by
the
reciprocal lattice translation.
this thing is going to come back here and it's going to look like this. So this is the reduced zone scheme. So now I get two branches within the first Brillouin zone. Those two branches are also called two bands. There are n
States here, n states here in the upper band.
and these kind of gaps
Exist between these bands. This is called a band gap, EG.
This opening up of the gap can be calculated, and it happens
Right at the edges of the first Brillouin zone.
It happens at the edge of every Brillouin zone. So these are bands that are formed. With a diagram, you get two bands. Okay? Sometimes this is called a valence band, this is called a conduction band. In phonons, when you study this problem in phonons, this is generally called an acoustic branch, this is called an optic branch.
The same phenomenon.
But for electrons, it's not called acoustic and phonon bands. There are four n
States possible here.
So if both of those atoms were monovalent, if both of those atoms there were monovalent, then this lower band will be completely filled.
You apply electric field, there's nowhere for the electrons to go. So the electrons, unless the field is so big that it rips off the electron and it excites to the high level, no conduction can take place. So it becomes an insulator. And when it's an insulator, even though it has free electrons, it's an insulator because the Fermi level touches the edge of this valence band. It has to overcome this gap to do conduction. So this is a kind of insulator which is called a band insulator. So no conduction can take place unless the churn effect happens. If you had two divalent atoms in that diatomic chain, right, then the upper band will also be filled. So you will have a jamming effect. No kind of conduction can take place because all the spots are already taken up. So conduction can actually be described by this phenomenon. Now, how do you control the bandwidth? How do you control the bandwidth? So there's another very nice picture that you can draw to explain this phenomenon, the formation of bands. So when can you control T? If the atoms are spaced far apart, what is T, large or small? T will be very small, right? T generally does depend upon the distance, depends upon the orbitals, which orbitals we're talking about as well. So if T is large, the atoms are far apart. When the atoms are far apart, T will be small, right? So you get tight bands. So if I were to draw a diagram, so if I had on this axis you draw the interatomic distance. Right. So the interatomic distance is kind of 1 over T in a sense. So far away I have an energy which is just the atomic orbital energy, EA. I'm talking about the energy per unit atom. It's EA. Right? The bandwidth is T is small, the band T is really small. This is really small. So this just compresses to a single energy level. Now when I bring the atoms closer together, the T starts to rise. When T starts to rise, bandwidth opens up. The bandwidth opens up. This level now goes into here. All the n levels are just compressed onto this level, so it's highly degenerate. So the degeneracy of this level is high. It depends upon the number of electrons in the system. Now you kind of bring the atoms closer together, the bandwidth increases. So all of these levels are now fanned out. They get this. So if I take a cross section here at this interatomic distance, I get one of these bands, right? I get this. I increase T further by bringing them closer, the bandwidth goes up. So all the n levels are now spread out. If I kind of map this onto this axis, I will get this diagram. So at even smaller distances, this kind of pans out. Okay, so these are bands. So this is a band that is formed. Energy is allowed to just in this regime between here and here, and there are n points in between. Those n points are the points that we have, the n finite space points that we have over here. This fanning takes place. This is how energy bands are formed. If I were to have this diagonal situation, the energies on the two kinds of atoms may be different to begin with. So I start off with these two energy levels. This is again their interatomic, let's call it S. Now this fans out, this fans out, and this fans out. Up till this point, there is a gap. There is a gap. So these are band insulators here in this regime. At this point, when these bands start to overlap, and this is a very important concept, then these band insulators become metals. because now the bands have overlapped. If this is completely empty, this is half filled and this is half filled, then these bands, when they overlap, they will be half filled. So half of this region will be filled and half of it will be empty, it becomes a metal. So at this point here, a metal insulator transition can take place. Okay? So this is simply as if you have two resonant circuits. The problem is that our students don't really know what happens in the laboratory, but I think these examples are really important. You have two resonant circuits, each one of them has a particular frequency, an RLC circuit, omega naught, far apart. They're different frequencies. When you bring them closer and closer together, especially if they're connected by a rod, some metal or iron rod, their frequencies will no longer be omega. There will be a range of frequencies, right? Or a transformer. So you have this mutual inductance effect in which one frequency then spreads out into a range of frequencies due to induction. Exactly the same phenomenon takes place. Two things that are far apart have their own energy, but when you bring them closer together, the energy is spread out. The degeneracy is lifted. Now, if this is the case of a 1D, not a Hamiltonian chain, but a 1D tight binding chain. If I were to I can also make this problem go into 2D. Let me set up that problem, and probably you can do this on your own. So, any questions at this point? So, in a 2D tight binding model, just as an example, suppose I have a square lattice and one orbital per atom. There's an atom here. So each of these sides is A. One orbital per atom. And the lattice is now square. Okay, it's 1 point per lattice. And now the case will be two-dimensional now, and I can write down the Hamiltonian for this in an exactly analogous fashion. But now, suppose my Hamiltonian is such that I include not only the nearest neighboring interactions, but the second nearest neighboring interactions. So, if I consider this atom is connected here and here. This is the nearest neighbor interaction. But this atom is also connected here and here. These are next nearest neighbor interactions. So the opposite sides are taken care of by the Hermitian conjugates. So if I were to write, and this interaction may have an amplitude minus t. This interaction may have an amplitude minus t prime. Different interaction at t prime, of course, is going to be smaller than t. Okay. So if I were to write the Hamiltonian for this, this would become minus t sigma and ij nearest neighbor interaction c I sigma dagger c j sigma minus t prime second nearest neighbor interaction. We go next to nearest neighbor interactions. C I dagger. Okay. Please do exactly the same calculation that I've done for the 1D. Yes. Apply the Fourier transformation. Go into the Fourier space and just take care of the deltas. There are two kinds of deltas. One is this delta, this delta for the nearest neighbor, and the next nearest one is this delta, and this is this delta. So just kind of define an x-axis and a y-axis. And be careful, okay? So if
if I were to solve this two-dimensional Hamiltonian, so I will get the energy dispersion relationship. Try to do this as a homework. Aman, please note this down. Minus 2t cosine kxa plus cosine of kya minus 4t prime cosine of kxa multiplied by cosine of kya ek minus k. Alright, so please do this on your own for a two-dimensional tight binding scenario. So let me plot this for you. Smaller, say 0.2, then I want to plot minus 2t into cosine of k, cosine of kxa. I take k to be 1 without loss of generality. Okay? Cosine of kx plus cosine of ky, right, minus 4 into t prime into cosine of 2k, cosine of kx, kx cosine of ky. I call this my energy. 8.8 का सर ठीक है so now I plot the energy and if I need to plot it 3D energy with respect to kx and ky. Now kx I want to plot the first Boulogne zone. What limits do I use for kx? Minus pi by a, which is pi, minus pi to pi. Kx from minus pi to pi and k. Right, so this is the curve. Right? So this is the dispersion relationship. There is a kind of bowl at in the middle of the Boulogne zone. Right? And it kind of it's I can also plot a contour plot. Right, so this is a counter plot. So plot the edges. Okay, so there is a hole in the middle of the Boulogne zone, and it just expands out. Now this is the energy dispersion relation for tight binding Hamiltonian. Now the point is that in order to understand ferromagnetism, we have to add another term to the Hamiltonian. What could that term be? That term captures the an additional potential energy of the electrons. So now we are considering only the tight binding Hamiltonian, that electrons can hop from one side to another. An electron can be located on one atom, that gives the bare energy EA. Now, how do electrons interact with one another? Can you have two electrons on one site? One location. So on site A, yes, we can have two electrons. Their spins need to be opposite. If they belong to the same atomic orbital, the spins need to be opposite, but you can have two electrons as well. But when you have two electrons on the same site, then there is a potential energy expense, a cost that you need to pay. Because now the electrons are in the same orbital, they are in the same region of space, they are close together, there is going to be repulsion, coulombic repulsion between those electrons, and the energy is going to go up. So, in order to add to this Hamiltonian, you need another term that captures the. So you have the tight binding Hamiltonian, which really represents the kinetic energy of the electrons because they're hopping around. Now there's an additional term which captures the electrons located on two electrons on the same site. So you have some energy associated with it called U, and then you have number density operator site I. Alpha spin up, number density of electrons on a site I, orbital alpha, multiplied by n I alpha spin down, sum over all I, right? In short, you can write this as U I N I up, N I down, okay? Or U sum of I, C I dagger up, C I dagger, C I dagger down, C I dagger. So you have this quartic term in the creation and annihilation operators. This is called the Hubbard term, and this Hamiltonian is called the Hubbard Hamiltonian. Now there's an interplay between the tight binding Hamiltonian and this term. As we will see in the later 1 or 2 lectures, this term gives rise to a Hamiltonian that has the same form as an exchange interaction. So this term, this Hubbard Hamiltonian, in certain regimes gives rise to ferromagnetism. Okay, so the tight binding Hamiltonian in tandem with this Hubbard Hamiltonian gives rise to the possibility of ferromagnetism. And this is what we're going to look at in the other lecture. So in the next lecture, we're going to derive what this U is. U is coulombic repulsion. So now we know what the Hamiltonian corresponding to the coulombic repulsion looks like. We want to take that to the Fourier transform. We want to take the Fourier transform of that. We want to take that to the K space. And then this will be a slight hint to Feynman diagrams of how you can do this from a quantum field perspective. We'll derive a form for U, magnitude for U, and look at the entire Hamiltonian together and see under what regimes would ferromagnetism be allowed. And why does that hold true for iron, nickel, cobalt, gadolinium, and dysprosium, which makes these the only 4 or 5 elements inside the periodic table which are natively ferromagnetic. Alright? Now, why do we give so much importance to just these 3 elements? Because without ferromagnetism, there will be no life as we see it today. There will be no electricity, there will be no luxuries that we enjoy, there will be no memory, there will be no computer programming, there will be no computer science major, there will be nothing. So it's actually iron which makes, and ferromagnetism that makes information possible, that makes electricity possible. So a physicist, even though one wants to become a cosmologist, should at least know this much about ferromagnetism. Right? So we'll kind of continue this discussion in the next lectures. Those who haven't
sent in their synopsis, final call to do that. And I'll upload the marks on Zamir, but I hope you've already checked with Hamas of what kind of